second topic is Bluepilling the Xen. It's the project that we implement on the base of the Bluepill source code. I will talk about it later. Then Bluepill is the code that allows Bluepilling the Xen hypervisor on the fly, and some words about Bluepill detection and how to detect Bluepill inside Xen. So that's a virtualization. Here we have a picture about a typical scenario that will happen if one of the nested virtual machines tries to enable nested virtualization. So in the bar you see a typical hypervisor, which is primary hypervisor like Xen, for example. It runs multiple virtual machines, and one of them tries to become a hypervisor. So if we allow that, we should somehow implement the support for its guests. Like these nested hypervisors should think that it's the own hypervisor present in the system, because original hardware virtualization extensions do not support this type of features. So this VM2 is a nested hypervisor. Consider it runs two virtual machines, like VM21 and VM22. And if the nested virtualization is implemented correctly, then we should allow unlimited depth of this nesting. So VM22 can become a nested hypervisor itself. So it will have two more guests, for example. So let's think how to handle this situation. So this is the picture of the relations between these virtual machines. So this is the arrows illustrate how should we route events from one hypervisor to another. Like VM221, for example, the lowest virtual machine in the picture, should be serviced by a hypervisor which runs in VM22, and so on. So the idea is to implement a flat scenario for one major hypervisor, which we call primary hypervisor. And from the point of view of this hypervisor, all these virtual machines are the same. So they all have the same privileges. So the details are very interesting because I said it before, CPUs do not support nested virtualization by default. So we have to implement some scheme that allows to correctly handle this. And let's start from AMD systems. So AMD SVM, the CPU extensions, implemented using a few instructions, like a few additional instructions. The main instruction is called VMrun, and it takes a pointer to VM control block as its argument. And this control block stores the state of the client which should be virtualized. So when VMrun instruction, when CPU encounters VMrun instruction, it stops the execution of the hypervisor and begins the execution of the guest until it meets some VM exit. Let's say we have to intercept RDMSR instruction. So if we set that we want to intercept this instruction in the VMCB structure, then it will generate, the CPU will generate VM exit, and it will return execution to the VMCB of VMCB 0 to the hypervisor, and then hypervisor takes some measures to service this instruction, and then runs this VMrun instruction again, and the guest continues. But what happens if the guest attempts to run a VMrun instruction? So basically, what happens with when the hypervisor has a guest that wants to be a hypervisor too? And this new VMrun instruction that the guest runs has its own argument, and it points to some another VM control block,
we will call it VMCB1. And of course, it will generate a CPU VMExit2 because VMRun is an obligatory intercept for AMD. And the main hypervisor will pop up, and then it should do something to run a service handler for this VMRun instruction. So the idea is to update this VMCB1 control block 1 with a few updates for handling another interceptions. Like VMCB structure holds a set of events that should generate VMExit, but we are not sure that all the VMExits that we want to intercept are set there. So we update this VMCB with another interceptions that we want to intercept as a main hypervisor, and we continue, and we should somehow continue the execution of the guest. And what should we do if this nested guest attempts to run our RDMSR instruction? So let's see what happens if this RDMSR instruction has to be intercepted by the nested hypervisor and, of course, by us. So how should we route this information about the interception? According to our scheme on the one of the first slides, all the VM control blocks share the same privilege level. So they all will, all the VM exits that happen in these control blocks will generate VM exits to the main hypervisor. And the main hypervisor will see that this RDMSR was generated by VMCB1 prim. So this VMCB, we created this VMCB especially for handling this nested scenario. It was not created by original main hypervisor, but it was created by a guest hypervisor, and we updated it. So we have to somehow inform the nested hypervisor that an event has happened in its guest. And to do that, we have to continue the execution of the nested hypervisor, the VMCB1, VMCB0, with the information about this event happened in its guest. And to do that, we emulate the CPU behavior, which is supposed to continue the execution of the nested hypervisor, of the hypervisor, right after the VMRun instruction. And the RAX register should be filled with the valid physical address pointer to the VMCB1. And we also fill VMCB1 with the event that was returned to us in VMCB1 prim. And this is why the nested hypervisor will think that it receives the event from its guest, because it analyzes the value in RAX register. There are some problems, though. It's not that trivial to implement this scheme. So in these white arrows show the places where general interrupt flag, a global interrupt flag, should be modified by the CPU. So this feature was new to the AMD architecture. It was released with hardware virtualization extensions, and this global interrupt flag should be set to 1 by the CPU on the first instruction that a guest is going to execute right after the VMRun instruction executed by the hypervisor, and it should be turned to 0 automatically on each VM exit. So when we see global interrupt flag set to 1 here, that would mean that the guest is going to to receive all the interrupts that happen in the system, in its virtual environment, of course. But on each VM exit, the CPU automatically clears it to 0. So we have to somehow emulate this scenario, because if we do not set global interrupt flag to 0 on every VM exit, then the nested hypervisor will receive some interrupts. It can receive some interrupts, but it might be not prepared to receive these interrupts. And this is why crash will happen. So how should we implement this behavior of the general global interrupt flag? This is the illustration of this behavior. So we have to modify the value of this global interrupt flag, but we cannot intercept its modifications. There are two instructions to do that, to modify the value of this flag. Set STGI and CLGI. So setting global interrupt flag and clear global interrupt flag. But we cannot, there is no field in VM control block to set or clear this flag, because it is global for all the virtual machines. So we have to modify the behavior of the interrupts, how interrupt come into the guest somehow. So we use, so we need to emulate this general global interrupt flag, and we use these valid interceptions for STGI and CLGI instructions. But our handlers for these instructions have to support the modification of the interrupt masking field inside VM control blocks. So in every CLGI and STGI handler, we modify these values in the VM interrupt masking. So we actually mask the interrupts in the guest. And we also handle DBs, and we modify these fields in the VM control block when the guest, when the nested hypervisor should receive the information about global interrupt flag, that it should be set to 1. So all the interrupts should be enabled. VM load and VM save also have to be intercepted, because they address the nested VM control blocks. We have to modify them correctly so that guest will get the valid information. The guest hypervisor will get the real information from them later. Also, it's a good idea to virtualize host saver via physical address, because it should not be modified by nested hypervisor. So it should be modified by the nested hypervisor, but we cannot change this value on the real machine, because there is no stack for these physical addresses. So we have to store each of them and then substitute this value in the intercept handler for the host saver via machine-specific register. What about ASID conflicts? Consider this scenario when the primary hypervisor has ASID 0 and it launches a guest, and assigns it ASID number 1. So ASID is a new feature from AMD which enables tagged TLB caches, so that VMexit should not will not generate a TLB flash on every world switch. But there is a limited number of these ASIDs. Currently, AMD supports 64 ASIDs from 0 to 63. And ASID 0 is reserved for the use of main hypervisor. So if we run a nested hypervisor in ASID 1, this hypervisor still thinks that it runs in ASID